Good evening, students. Am I audible?
Yes.
Okay. I'm just going through the revised syllabus. And I'll be sharing it here. We'll have a look at it and then we'll proceed.
Sir, a small doubt, sir. So if it's MCQs, then derivations can be kept it, sir.
Niklesh, are you using any mic for speaking? Are you wearing
No,
any
sir.
headphones around you?
No, sir.
Okay. If you can just go little away from the mic and speak, your voice is there is some
Yes, sir.
clarity lacking in voice.
So
Yeah.
if it's MCQ, then can we skip the derivations? Not, sir.
You can actually. That is what even I'm thinking. There's a first time this kind of a pattern is coming. See, I'm only concerned about the consequences. Whereas if you skip the derivations, but I suggest you to study. Okay. Don't miss it
Yes.
because I'll tell you one advantage. See, generally when I advise everybody who's preparing for competitive exams, right? So we know that competitive exams are mainly MCQs, right? Let's think in this way. So what happens is competitive exam, you have 36 chapters or 30 chapters, 11th and 12th put together. You have to remember 30 chapters, right? So all of a sudden, what will happen if there is a problem and there is a formula which is slightly tricky, right? So try to understand. If there is a slightly tricky formula where you get confused between plus and minus, that is the point where derivations will help you. You have to understand. Suppose, let's say, in the exam hall you suddenly got confused. And there is a problem where the options are also confusing. You have a plus, so you will get both the options. If you use plus, let's say you will get option A. If you use minus, you will get option B. Where, in spite of knowing things, will you not be in a danger zone?
Yes. Yes, sir. Yes.
Okay, so I generally don't suggest anybody to skip. A competitive exam, I suggest them to study. So when it is CBSE, yes, I would recommend you to study. Maybe you can do one thing. What you can do, you need not study like exactly because you're not going to write subjective. You need not study in the way that where you need to replicate the exact content in the paper. But at least practice it in such a way that if you are in a situation where you are forced to recollect the formula, you at least remember the steps and you're able to arrive at the right conclusion. Okay. So I'm just saying for the sake that is the thing. But yeah. So I've just opened this document. I hope you guys are able to see, right? So electric charges and fields, yes, we have completed everything. It's something similar to last year only. If you see, they have removed the electric field due to a spherical shell. That part is not. So except that you have everything. Right. Similarly, in the case of electrostatic potential and capacitance, I don't think anything is skipped. No, nothing. There is no omission in this. Okay. Then what about current electricity? In current electricity, if you see, this meter, bridge, and potentiometer, they are saying only qualitative ideas. Means maybe they are expecting you to know only the formulae because both are experiments. Right? So you're not going to draw or do anything. So maybe they're expecting you to solve only the problems. So with respect to moving charges and magnetism, so by itself, yes, application to current carrying circular loop. Yes, you have to remember that formula. Ampere circuit law, only qualitative treatment. To remember the formula and solve problems. Suppose on this thing. So there is also almost no deletion. So I'm going to conduct a test, right? Next week on 6th, I think, right? 6th of August is the date that I gave. 6th or 7th, or whatever it is. That Saturday, that will be a subjective test. Many of them had been asking me. So that will be a subjective test because I want to know how much you guys have understood this concept. So yeah. So magnetism and matter, almost everything is there. Magnetic elements, Earth's magnetic field and magnetic elements means that magnetic properties of material is there, right? That susceptibility, those things, those terms are there, no? Magnetizing field intensity. That part is omitted. That is the magnetic properties of materials is omitted, is deleted according to the syllabus for me to explain you. But I would suggest you not to ignore this because there are certain questions which can be asked in the case of self-induction and mutual induction for which you need this knowledge. Okay. So I would not suggest you to skip it, just go through it. So in electromagnetic induction, if you see, yes, basics, Faraday's law, induced EMF and current, Lenz's law, eddy currents is there, AC generator is removed. Exactly, we discussed it yesterday only, or else we would have completed this chapter. But anyways, AC generator is important for you to understand the connectivity to the next chapter. Because you'll not understand why that E naught sine omega t and all came. Okay, anyways, we had time, so we discussed it, it's fine. You can just go through the concept. Yes, maybe you need not practice those diagrams and all those things. So those kind of theoretical topics, I don't suggest you. That I will not suggest you to sit and practice. But yes, derivations you definitely need to do. Sure, yeah. So it is eddy currents that we need to discuss. Correct, Ada? I think everything else we have completed. La? Is there anything that is left out? So I have a guess of what kind of questions will come from eddy currents also, but it's better. I'll show you a small activity based on this. I'll explain you the concept. Seriada. After that, we are ready to go with alternating currents. Okay, this will maximum take 4 or 5 classes. So what is today? Tuesday, no? Wednesday we'll have a class. Next by next Wednesday is maybe we'll complete term and portions itself. Maximum. Okay, shall we get started? Guys, are you there?
Yes, sir. Yes.
Okay. So eddy current. I'll show you a small activity. Okay. So there is a concept called as braking pendulum. Okay. So braking is not B-R-E-A-K, it is B-R-A-K-I-N-G. It's a mechanical system. Okay, you know what are brakes, right? Like generally you have a car or any vehicle has brakes associated with it, where we will apply things mechanically to get the output. Right, now listen to this. I'll show you this activity. So eddy currents and magnetic braking of pendulum is what we are going to see. Okay, I want you to observe it clearly what is going to happen.
I would like to do another demonstration of eddy currents.
This is a magnetic source. You are able to see it. You have seen something like this already. I explained this when I showed you paramagnetic, ferromagnetic, and other substances, right? Now, diamagnetic substances. I showed this magnet. Into this magnetic field, what will happen is a paramagnetic substance, okay? A substance, it can either be a paramagnetic or a diamagnetic substance, will be forced into this. You have to observe what is going to happen to that paramagnetic or a diamagnetic substance as soon as it enters this particular field. Okay, so that is what we are going to concentrate upon.
The resulting magnetic braking that will occur on a pendulum. So what I have here are two magnets. Okay, so this is like the North Pole here of this magnet and the South Pole here of this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if this were a piece of steel, it would stick, and I probably wouldn't be strong enough to pull it apart.
Tell me one thing, guys. If I put a steel material in between these two poles, what do you think will happen? Guys, are you there? I'm asking, between these poles, let's assume you have a steel material in your hand. What would have happened if you have just put between them? Then that steel is a ferromagnetic substance, right? So steel would have gone and got attracted to either of the poles. That would have happened. Correct?
Yes.
Right. Now see, if you put a paramagnetic or a diamagnetic substance, it is not going to experience that level of attractive or a repulsive force.
But what I have here is a piece of aluminum. Okay, so aluminum is paramagnetic, so it is only weakly magnetized, so it's not really attracted to the magnets.
So he has an aluminum.
Okay, so
like a vessel kind of thing, or whatever I can say. It's a swing actually, which is going to be projected between these magnetic poles.
I also have two other pendulums. Okay, this one has slots in it, and this one, the slots go all the way to the bottom, so there's no connection along the bottom. Okay, and any of these I put in here will freely swing.
So what is happening when that aluminum is hanged and it is taken to a certain angle and left? It started swinging, correct? Why did this happen? Why is it swinging? Which force is actually, so if you leave it, which force is actually trying to bring it down to the equilibrium position? Sorry, it is the gravitational force, right? So that gravitational force is what is putting the object into this kind of a swinging motion.
Okay, so now let's see what happens when...
Now, see what happens to that gravitational force when the same object is projected into an external magnetic field.
I try to swing this one through the magnetic field.
What happened?
You notice how...
So it is getting stopped, right? It is not able to cross it, right? That is when it is a complete aluminum, right? He showed two other slots, aluminum pieces also, where there were certain slots available on it, right? Let's see what happens to them also.
And stops. Now, if I did the one with the slots...
So this is the one with close to slots. What happened?
We see it also breaks and stops. Not
it is stopping,
quite
right?
as quickly.
But what is the difference
and
between
finally,
the previous one and this one?
There was no magnet involved.
Think
the previous case, when it was a complete aluminum thing without these holes, without these slots.
More flux was there here.
Yes, it stopped faster, whereas this one is slightly taking some time to get stopped. Correct? Now, what do you think will happen with the open slots
with
one?
the grooves, so that there's no...
What do you think will happen with this?
Even more time.
It will take more time to stop, right?
Yes, sir. Yes.
But observe.
No connection on the bottom.
Nothing is
swings
happening
freely. Okay, what is happening is that as this one is swinging into the field, you have a changing magnetic field in this region.
Did you understand what happens? Right. This is what we need to give a theory to this, right? And that theory that we are going to give is what is called as eddy currents. Okay. What do we call them? We call them as Yes. So we call I'll write it here itself. We call it as eddy current, or sometimes it's called as Foucault current, or sometimes it is also called as circular current. Okay, all the three mean the same. Okay, so what exactly is happening is when the magnet is present, right? When the magnetic field is present, and as soon as this aluminum rod is entering in this direction, okay, it is having a velocity in this direction, right? Now, what is happening to the area? What is happening to the flux? Is it increasing or decreasing? What is happening to the flux?
Increasing.
It is increasing, right? We already know the logic. Here, the paper is acting like the South Pole. So you are acting like the North Pole, correct? So when the flux is increasing, what pole should get generated? It should be North Pole. So North Pole means what will happen is as the whole metal sheet is entering into the magnetic field, there will be small loops of current. There will be small loops of current. 1 minute, wait. Did I put it in reverse? Yes. There will be small loops of current like this getting generated in circular paths, and these currents are what are called as eddy currents, and they are the ones which are responsible for producing the opposite flux, as a result of which the system is coming to instantaneous rest. Are you able to understand? So that is what happened with the solid steel, solid aluminum. Whereas the one which where there were these kind of slots. So these kind of slots were there. No, there also eddy currents got generated, but due to this cavity, the amount of eddy current that got generated was less compared to the case number 1. Okay. Whereas what happened in the third case, which was like in the comb-like structure, there was no eddy current formed, because for the eddy currents to be formed, they are supposed to be in circular loops. Whereas you see here, there is a gap, right? So due to this gap, what is happening? The eddy currents were not generated and they did not come to rest, and they were in continuous motion. Guys, am I clear? It's actually a very simple concept. You know, if I have to give you a real life application of this, okay. So you guys would have gone in exhibitions, right? In exhibitions, you have this ride called as roller coaster. We have a roller coaster, right? Yes or no? So it is going to be something like this, right? Which are designed on a rail track. So when you sit here, have you ever observed here you're falling under the gravity, right? Let's think of it. You're falling under the influence of gravity, right? As soon as you reach this point, your kinetic energy will be more, right? If this amount of kinetic energy is there, which is making you climb in the upward direction, then what will happen is due to sudden jerk, you might even fly out of that place. If that is the amount of kinetic energy it is going to have. So what is necessary to be ensured there? Though you're falling under the influence of gravity, you need to ensure that the coaster, you need to ensure that the machine is getting slowed down at that particular point, at the bottommost point, so that you go up with a limited amount of energy, but there is no person to control it. Are you pressing any brake there? No, right? So how is it happening? It is happening due to the same principle. So they make use of this eddy currents to bring in those braking systems at that point. But a complete halt also is not needed. It is only to slow down the process. So to slow down the process, what they do is they create some short kind of things and design something according to the requirement of amount of eddy currents to be produced. Are you guys able to understand? That is why this is also called as a braking pendulum. Guys, are you there with me?
Yes.
Got it? So this is all about eddy currents, guys. Let me read the textbook. So there is only one page that you need to read. So whatever story I told you is already there in it. The eddy currents. So I told you, Foucault. Okay. So what are the applications of eddy currents? They are used in the magnetic braking trains. They are used for electromagnetic damping. They are used in induction furnace, and they are used in the electric power meters. These points I want you to read. It's full of theory. There is nothing much for me to explain in it. Okay. So this is all about electromagnetic induction. Guys, is there any doubt from this chapter? This is all about this chapter. We're done with it. Okay. Shall I move on to the next part? So the next chapter that we are going to discuss is called as alternating current, and the base for this chapter comes from the last topic of the previous chapter. What was the last topic? Actually, it is AC generator. In AC generator, please look at your notes and tell me how is the value of EMF defined? E is defined as E naught sine of omega t. You guys remember this? Where E stands for what? It is the instantaneous EMF. E naught stands for the peak value. Omega stands for the angular frequency, and T stands for the time. Right? So this is going to be the base of this chapter. And the difference between the third chapter and this chapter is, third chapter we were completely dealing only with direct current. Here we are going to deal only with alternating current. So what are all the topics that we are going to cover in this chapter are: what will happen when you apply AC voltage across a resistor, what will happen when you apply AC voltage across inductor, capacitor, and there is something called as phasors and phasor diagram that we are going to see. Then what will happen if you apply AC voltage to a combination of resistor, inductor, combination of resistor, capacitor, combination of inductor, capacitor, what is going to happen to it? Similarly, we'll see the power in the AC circuit, LC oscillations, and transformers. Okay. So before that, we need to understand certain basics. I told you yesterday, right? We in our house, what is the voltage that comes?
230 volt.
230 volt is there. No, the 230 volt is actually the alternating voltage, right? And the 230 volt is actually called as an RMS value. So first we need to understand what is the difference between average value of AC and an RMS value. It is then we are actually going to get to the main context of this chapter. If I directly start what will happen when AC is connected across resistor, you're not going to understand anything. Okay. So let's get started, guys. Alternating current. So an alternating current is basically that current whose magnitude changes continuously with respect to time and direction. Okay. So in contrast to it, what you have a direct current, that is a current which flows with a constant magnitude in the same direction. So to put it in simple terms, bidirectional currents are called as alternating currents, and unidirectional currents are called as direct current. positive, negative, this thing. Okay, so unidirectional currents are called as direct current. Why I'm saying this unidirectional is because in the 14th chapter, you will see some current like this. Is this alternating or direct current?
I think
Alternating.
magnitude doesn't change.
It is direct current. But the thing is, if you look at an alternating current, it has a positive cycle and a negative cycle. They are two directions. So if the current is moving in forward direction, you call it as positive. Current moving in the opposite direction, you call it as negative. Whereas if the current is completely moving with a positive cycle, that is called as direct current. And this is generally called as a fluctuating direct current. That is the only difference. Okay. So there is this kind of a problem where we will see in the 14th chapter, for which we will find a solution also. Okay. Next. We know that when a coil is rotated in magnetic field, an alternating EMF is induced in it, which is given by the relation E is equal to E naught sine omega t, which I have already told. Now, if this alternating EMF is applied across a resistor, then according to Ohm's law, we can say I is equal to E by R, and the current in the circuit will be E naught by R times sine omega t. So I is equal to I naught sine omega t. Okay. So EMF is also varying as a function of time, and current is also varying as a function of time, and both are happening sinusoidally. So what is the meaning of sinusoidally? It can either be a function of sine or cosine. So many people sinusoidally means they think it should only be a function of sine. No need. Because cosine is complementary of sine. So that is also called as a sinusoidal function. Okay. And is called as alternating current. Is there any doubt till this case? Is there any point that you didn't understand?
No, sir. Clear, sir.
Good. Okay. Where I is called as the instantaneous value of AC. This I is called as instantaneous value. I naught is called as peak value. Omega is called as angular frequency. T is called as any instant T. So this E naught by R is called as the peak or maximum value of AC and is called as the current amplitude. Okay, so what is the meaning of amplitude? Amplitude is nothing but the maximum value attained by an alternating current in either direction. So this point is there, no. This height is what is called as I naught, and this height is also called as I naught. So the maximum value attained by an alternating current in either direction is called amplitude or peak value and is denoted by I naught. Similarly, what is time period? So time period basically means the time taken by the alternating current to complete one full cycle. Right? So how do you define time period as? Time period is defined as 2 pi divided by omega. That is the angular displacement in one cycle divided by the angular velocity. So T will be equal to 2 pi divided by omega. Okay. Next. What is frequency? Frequency is a reciprocal of time period. So if T is equal to 2 pi by omega, F will be equal to omega by 2 pi and omega will be equal to 2 pi F. Okay, there is a frequency. Now this is where some important concepts are. See, generally whenever you have values which are function of time, okay, then you can calculate the average value of it over a complete cycle. Okay. So the first point that we are going to see is average value of AC over one complete cycle. How much is it going to give us? Look at the way I'm going to calculate it, okay? So we know that I is equal to I naught sine of omega t. I have a question, guys. See, if I give the values between 0 to 50, or let me say 1 to 50, so 1, 2, 3 till 50, all natural numbers are there. If I ask you to calculate the average of all, what will you do? 1 plus 2 plus so on till 50, the whole divided by 50, the total numbers that are there. Right. So you can do this kind of an operation when you have discrete numbers in your hand. So can I write it like this? Sigma xi, where I is equal to 1 to 50, the whole divided by 50. Yes, sir. Can I call this as average value of all the numbers? In a similar way. Tell me. Tell me. Right? Now see, what is our job? Our job is to calculate the average value of AC over one complete cycle. Okay. So this is 0. This is what is called as one complete cycle. Okay. So average value of AC over a complete cycle is something like this. Instead of sigma, I will replace it with integral. Integral of, it starts at 0 and it ends with one time period. This is t by 2, this is t, this is 0. So 0 to t, I naught sine omega t dt, the whole divided by integral of dt. Okay. This is what is the mathematical expression for average value of AC over a complete cycle. Okay. Now, when you calculate the average value, what will you get? I naught into integral of sine omega t dt between 0 to capital T, the whole divided by capital T. So this will be I naught into, or I naught by t into, what is integral of sine? Integral of sine is minus cos. So minus cos omega t divided by omega between 0 to capital T. Okay. So I naught divided by omega t into minus cos omega capital T plus cos 0. So it will become I naught by omega t into minus cos of, what is the value of omega in terms of time period, guys? 2 pi by capital T into t plus cos 0. Okay. So I naught divided by omega t into t and t will get cancelled. Cos 2 pi is 1. Minus 1 plus 1 will give you a 0. So what I'm trying to say is, when you calculate the average value of AC over one complete cycle, then its value is going to be 0. Guys, are you noting it down? Any doubt till this step?
No, sir.
Okay. Moving on to the next point. So, if you observe the average value of AC over a complete cycle, it is 0. Okay. Then, average value is generally not calculated for full cycle, rather the average value is calculated only for half cycle. And for the half cycle, they are given a definition like this. So, average value of AC is defined like this. It is defined as that value of direct current. So, I told you, right, there are two values. One is called as average and RMS value. And average value of AC is related to DC. Okay, how it is related? See, is defined as that value of direct current which sends the same charge in a circuit in the same time as is sent by a given alternating current in half of its time period. Meaning, if I have a bulb like this, okay, and there is an alternating source connected like this, and I have the same bulb where I have connected a DC source. Okay. In both these cases, what will happen is this is also going to send charge, this is also going to send charge. Let's say you have a stopwatch in your hand. In the time period, in the time of t by 2, let's say it is sending a charge Q. In the same time t, if this is also able to send charge Q, let's say this is 5 volt. Okay. The battery, the DC source that you have connected is 5 volt. And here the AC source is 230 volt. Okay. Or it's not 230. Let's say it is 310 volt. Okay. Where 310 volt is the peak value. Try to understand this. Where 310 volt is the peak value of this alternating source. Then I can find the average value of this and say it is exactly equal to 5 if the charge sent by this alternating source and the charge sent by the DC source is the same time of t by 2 is the same. Okay. So what I'm trying to say is the average value of AC in this case will be equal to 5 volts. So how did I get that 5 volt? Because I have to just take the definition of average value and equate it to the exact DC source that I have. Guys, did you understand this? So as I told you, average value is calculated only for half of the time period. Okay. So if you're clear with this, I'll go to the next concept. Now the question is, how to find the relation between average value and peak value of AC? So how you do is, I average, okay. So we have learned a lesson that the average value over a complete cycle is 0. So average value is calculated only for 0 to t by 2. And what is the value of it? It is I naught sine omega t divided by integral of dt between 0 to t by 2. So if I take this I naught outside and divide it with t by 2, then I'll have integral of 0 to t by 2 sine omega t dt. Okay. So this will be equal to 2 I naught divided by t into, what is the integral of sine omega t? Just now I told you. Minus cos omega t divided by omega between 0 to t by 2. So 2 I naught divided by omega t, and take the minus sign outside, it will be cos omega into t by 2 minus cos 0. So it is minus 2 I naught divided by omega t into cos of omega is 2 pi by capital T into t by 2 minus cos 0 is 1. So t and t will get cancelled, 2 and 2 will get cancelled. Minus 2 I naught divided by omega t into cos pi minus 1. Cos pi is minus 1 and there is another minus 1. So this whole thing will give you minus 2. Okay, multiply both. You will get 4 I naught divided by omega can be written as 2 pi by t into t. T and t will get cancelled. This 2 and 2 will get cancelled. So 2 I naught by pi. Okay. And this 2 by pi times I naught is what is 0.63 times 7. Okay, so if somebody asks you what is the average value of a given AC source, then you need to multiply the peak value with 0.637. Make a note of all these points. Guys, if there is any doubt, get it clarified. Nobody is responding, and this is a tough topic. Let me know once you are done. Done? Guys, I need some response. Okay. Now listen. Now the next one is called as the RMS value. So what do you mean by RMS? It is called as root mean square. Okay. So this root mean square is also called as effective value of an alternating current. How it is defined, we will see it later. Let's see first how to calculate it. Guys, I want you all to concentrate. This is a very, very, very tricky one. Okay. And I know you guys have not yet learned integration. This one involves a slightly tougher integration also. So what is the instantaneous value of current? I is equal to I naught sine omega t. Okay. So RM is, what did I say? It stands for root. So what root? I'm talking about square root. Square root mean square. Okay. Means I need to take the square root of mean means average of the squares divided by n. X1 square plus x2 square plus so on till xn square divided by n. So Here what I will do is I will write I RMS or I effective or I virtual is equal to square root of integral of 0 to t I square dt the whole divided by integral of 0 to t dt. Make a note of this point. This is what is called as IRMS. Okay. Now listen. Square root of. So I'll take the square root at the end. Okay. So I square is I naught square sine square omega t, the whole divided by t, where integral of 0 to t comes. So what will come out of the integral? I naught square divided by t into integral of 0 to t sine square omega t dt. Okay. I naught square by t into what will happen is the sine square omega t is there. Right? The sine square omega t, you don't have a direct integral for it. So what you do is you write it as 1 minus cos 2 omega t divided by 2 times dt. 1 minus cos 2 omega t divided by 2 into dt. I naught square by t into. Now what will happen is integral of 0 to t dt by 2 minus integral of 0 to t cos 2 omega t into dt divided by 2. Okay. So I naught square divided by t into 1 by 2 into this will be capital T minus this will become 0. Okay. So this t and this t will get cancelled. I naught square by 2. All these things are supposed to be under a square root. So this will become I naught divided by root 2, and this is the most important thing. This I naught divided by root 2 is what is 0.0707 times I naught. Okay. So I RMS is 0.707 times I naught and I average is 0.637 times I naught. Out of both, it is the RMS value which is the most important one. Okay, make a note of all these points. Okay. So let me explain let me give you the definition of this. So I RMS is, it is defined as that value of direct current which produces the same heating effect in a given resistor as is produced by the given alternating current when passed for the same amount of time. So write down the definition for it. It is defined as that value of direct current which produces the same heating effect in a given resistor as produced by a direct current as produced by, as produced by the alternating current when passed for the same amount of time. Okay. Now, listen guys. So the questions can be asked like this. So IRMS is, let's say, 230 volt. Then what is the value of I naught? Do fast and tell me. So what is the answer, guys? 230 into root 2 or 1.414. So this is the value of I naught. Okay. So generally, if they give you a question and they say the alternating current is of this much value, the voltage is given to you, then they have given you the RMS value. Okay. So this is about average value and RMS value. So the important summary that we can draw from them is, what is the value of I average? It is 2 divided by pi times I naught, and I RMS is equal to 1 divided by root 2 times I naught. Okay. So the 230 volt at our home is what? Is the RMS value. Okay. Guys, are you able to hear me?
Yes.
So this is all about the average and RMS phase. So tomorrow we'll be discussing about a very, very important concept, which is phasors and the phasor diagram. There I'll be explaining the concept of leading and lagging. Okay. So to understand that, we need to know what are phasors and phasor diagram. That will start tomorrow. I suggest you guys to revise this in before tomorrow's class. Okay. Any other doubt from today's class?
No.
Okay, we can wind up.
Thank you.
Yeah.
Thank you, sir. Thank you, sir.